Hello, I'm Matthew Winter, and I'm really excited for us to begin our review of the time value of money. This lecture will be split into two parts to hopefully make it a little bit easier for you to pause and follow along. And as always, the intention and the structure is that once you see the material, you pause it and try to solve. Our last lesson provided a general overview of the course. This week, we're going to delve into chapters 1 and 4 and touch a little bit on some material in chapter 7. So we'll go over the fundamental concepts in finance. We'll look at the future value, present value, and finding the proper discount rate. We'll calculate how do you find the present value of a perpetuity, an annuity, and a growing perpetuity annuity. And then lastly, we'll look at amortization, which is paying off a loan bit by bit. So let's start with our present value equation. Here we have the value of the firm, and the way that we estimate these free cash flows, we have our net operating profit after taxes. So that's our sales revenue, less the cost of us actually earning that revenue, less what we have to pay for taxes. We then subtract the required investments in operating capital. So how much do we have to spend in order for the firm to continue to operate and generate these cash flows? Everything else that's left on the table is the free cash flow. That's the cash that's freely available to our investors, our shareholders, and our creditors. When we value the firm, you would do this if you were an analyst. You would do this if you were in private equity. You would do this over and over throughout all of your applications of corporate finance. When you go to value the firm, you're basically treating the firm as if it's a perpetuity. You're taking the summation of all of these expected future cash flows, and each one is discounted by the appropriate WACC for that time period. So let's look at that timeline. When we look at the timeline, we have time 0, think of that as today, and then 1, 2, and 3. So 1 could be next year, it could be tomorrow, it could be next quarter. It all depends on the timeline and the frequency with which these cash flows are arriving. Typically, we'll look at it on a yearly basis, but it can also very easily be on a quarterly or monthly basis. At I, that interest rate, that's the discount rate at which your cash flows are either compounding or the rate at which they need to be discounted across these periods. So our first concept is going to be the time value of money. Suppose your risk-free bank account pays 5% per year. If you deposited $100 today, you would have 105 in 1 year. So the future value, FV subscript 1, is going to equal that 100 multiplied by 1.05. Alternatively, suppose we'll receive 105 in 1 year in our risk-free bank account, and the discount rate is 5%. What is that 105 worth today? That 105 would be discounted by 1.05, and today would have a present value of $100. More generally, what if you deposited some value, PV0, so some present value today, and held it into your account for T years? More generally, we know that the future value at time T is going to equal the present value today multiplied by 1 plus R, that's our discount rate or our compounding rate, to the power of T. Alternatively, we can always solve for the present value today if we know our future value and we know our discount rate and our time periods. So let's apply this. Suppose your interest rate was 10%. After 1 year, you put in your 100, you would get out 110. After 2 years, you put in your 100, it's going to compound and you get out 121. In 3 years, and so on and so forth. So what we can see is that within all of this, there's a generalized formula that's basically at play. Our present value equals our future value discounted back according to the time periods that it's in. So if we plug in our numbers for our example of future value at time 3, given the present value of 100, and an interest rate or a discount rate, a rate of return of 10%, over 3 periods, it's going to compound to 133.10. And we can also use that present value and future value formula to try to figure out what's known and what's not known. So what's the present value of $100 due in 3 years if my interest rate, my annual interest rate is 10%? So what do I know? I know that today is time 0. I know that in between each period, my actual values are compounding by 10%. And lastly, I know that at the end of 3 years, I'm gonna get $100. So how do I solve this? First, we're gonna figure out how to actually put things into that present value formula, and then we're gonna solve. So if I rearrange my present value formula, I know my present value today equals my future value discounted back across these time periods. What's my future value? In this example, it's 100. What's my discount rate? In this example, it's 10%. So when I plug these in, and remember, you always want to remember your order of operations. So here that applies to doing these steps first. You always want to do your parentheses first, and then you want to take your exponent to that. Okay, so let's keep it going. Suppose I put in $1 today, and I know that my interest rate is 20%. I want to know, how long do I have to keep that dollar invested in order for my money to double? So how long will it take to double your money? Okay, so I know my future value that I want is going to be 2. I know my present value is 1. And in this example, I know my interest rate is 20%. What I don't know is my n. So we'll set it up and solve for n. On my left-hand side, I've got $2. On my right-hand side, I've got $1 plus 1.2. That 1.2 is my interest rate. It's how it's going to compound. And n is the number of periods through which this will compound. That's what I don't know. So when I follow my order of operations, I do my parentheses first and I rearrange my terms. Now I've got 1.2 to the n equals $2 over $1, which equals 2. That's very straightforward. Now, in order to get my n from the exponent, I need to use my natural logs. So if I take the natural log of both sides, I've now got n multiplied by the natural log of 1.2 equals the natural log of 2. I can solve down for n. The natural log of 2 and the natural log of 1.2, those are just numbers, and that's what we see on the very last line. N equals 3.8. How did we get there? Well, we had everything that we needed to know. In this example, we knew we put $1 in. We knew that our future value was going to be 2. We also knew our interest rate, but what we didn't know was the number of periods through which we would have to keep our money invested. So let's move on. More generally, when we think of our time value of money, we can sort of have 2 kind of very standard ways of looking at these expected cash flows. So one would be an annuity. If I have a constant stream of C dollars paid for T years starting next year, it's going to have a present value equal to this annuity formula. There are 2 things that I want to point out. First is that we always say starting next year or starting next period. Your annuity formula and your perpetuity formula are always giving you the present value of a stream of cash flows that start in the next period. So for our first example, when we have those cash flows that are compounding at a constant rate, and we know that it's going to be for a limited amount of years, a finite time period, that's an annuity. If we have that constant stream of C dollars and it's paid forever and ever and ever, it never stops being paid, then we have a perpetuity because those cash flows are going to be going on perpetually forever. Notice how that perpetuity formula, the present value of those future cash flows that are all discounted, looks very similar to our value formula from slide 3 when we looked at the value of the firm. So let's apply these and kind of make sense of it. Our first example is going to be an annuity. So this is the timeline for an annuity that's going to pay you $100 every single year for 3 years. In order to calculate the present value of this annuity, I need to know what my interest rate is. So let's plug in an interest rate and see what we get. An annuity will pay $100 for each year for 3 years, and the discount rate is 10%. What is the present value of these cash flows? Now, there are 2 ways we can approach this. We can create a timeline, discount the cash flows, and then add them up. And maybe this is the approach we would want to take if we only have a few cash flows to discount. Alternatively, since our cash flows and our discount rates do not change, we can apply the annuity formula. So we'll take both approaches and we'll see what we find. If we do a timeline, what do we have? We know at time 0, that's today, we're trying to find the present value. At time 1, we get 100. At time 2, we get 100. At time 3, we get 100. And what are we doing? The 90.91 is 100 divided by 1.1. The 82.64 is 100 divided by 1.1 squared. And the so on for the 7513, that's 100 divided by 1.1 cubed. We add those up, we have our present value. Alternatively, we could plug our numbers into our annuity formula. We have a constant cash flow of C. We know that's going to be 100. Our N, our time period, it's going to be 3 years. That's 3. And we also know our R. Our interest rate was 10%. Notice how both approaches yield the same answer because they have to. Okay. An example of an annuity. A great example of an annuity that you probably have never thought of would be a mortgage. A finite life project is also a good example of an annuity. A finite life project means that the firm is going to undertake some investment that's going to have a stream of revenue for a fixed number of years. An example of a perpetuity, in the UK, you have consul bonds, where more generally, if there's some long-term debt that the firm is just continually rolling over. So the firm never pays off the debt, but they just roll it over. The way that we value real estate, we think of it as a perpetual stream of dividends and rental income, and it's also the way that we value stock. We think of the stock as a never-ending stream of dividends and cash flows that are discounted back to the day. So let's do some examples. An example of an annuity. Your new 30-year 5% APR mortgage requires payments of $40K per year starting next year. How much does your house cost? Okay, 2 things you want to remember when you set this up. First, you know your N. In this example, your N is going to be 30. You also know your discount rate. In this example, your annual percentage rate is going to be 5%. And lastly, you actually know your C. In this example, the constant stream of cash flows that you're going to pay out is $40,000 per year. So when you set this up, you have everything you need to solve this as an annuity. Question B, what would be the value of this house today if you had to start making your payments in exactly 5 years? So here it gets a little bit tricky, but there's one thing I want you to remember. Your annuity formula is going to tell you the value of these cash flows starting next year. So what's the present value of all of these cash flows starting next year? You plug it in and you can solve for the present value of your home. Now, if it's going to start in exactly 5 years, I want to discount that back, but I want to be careful. So make sure that you're careful. You don't want to discount it back by 4, or sorry, you don't want to discount it back by 5 because you're looking at a stream of cash flows that are going to start in the next time period. So you're going to take the present value from part A that you solved for, and then you're going to discount that by 1.05 to the 4 when you solve part B. You want to pay off your $1 million home over 20 years starting next year using a 6% APR mortgage. How much do you have to pay per year? Well, in this example, I know my present value, that's 1 million. I know my 6%. I know 6% is my discount rate. And I also know my M, that's going to be 20. So I plug in everything to my annuity formula, and then I solve for my C. Let's do an example of a perpetuity. Your family has a perpetual trust, so it's a never-ending trust that pays $100,000 per month starting next month. The fund is in an account that offers 1% interest per month. How much is the fund worth today? In order to value the fund, I want to take that 100K per month that gets paid every single month, and I want to divide that by my discount rate, my 1%. So my 100K divided by my 0.01 is going to yield my answer. Part B, suppose instead that the fund begins with 100,000 per month in 13 months. How much is the fund worth today? So here for part B, I want you to be mindful of how you were mindful in part B of example 1. Notice, whenever you have a perpetuity or an annuity, you're always looking at the present value of cash flows that start in the next period. So in this example, if I know that my 100K per month starts in 13 months, then I want to discount that by 1.01 to the 12. The reason why it's to the 12 and not to the 13 is because in part A, when I solve for the present value of my perpetuity, that is the present value of these cash flows that start next month. So I already know how this will be valued if it starts next month. If it's going to start in 13 months, then it's going to be discounted by 12 and not the 13. So this is going to conclude the first half of our lecture. And the next half of our lecture, we're going to look at growing annuities, growing perpetuities, NPV, and amortization, which is slowly paying off a loan bit by bit.